Hello students, in today's lecture we are going to study NCERT section 8.4 to 8.5.1 and we will also solve an example 8.1 from the chapter named Mechanical Properties of Solids. This is our disclaimer. Learning objectives. By the end of this lecture, you will able to understand the concepts of stress strain curve, elastic moduli and Young's modulus. So in today's lecture, we will cover first 8.4 stress strain curve. After that, 8.5 elastic moduli. And then 8.5.1 Young's modulus. And last, we will solve an example 8.1. So, let's start. Stress strain curve. Graph that shows the relationship between stress and strain for a material gives important information about its elastic and plastic properties, known as stress strain curve. So look at figure here. On y-axis having stress and x-axis strain. Notice how the curve starts off straight, showing elastic behavior, then bends as the material yields and eventually breaks. We will discuss each part of this curve. O to A to B, B to C, D to E. Each part of this curve in detail. So pay attention to how the shape changes as stress increases. Alright. So here study the stress strain curve. So analyzing the points of stress strain curve. Each point or region on this curve represents a different way of materials respond to stress. Understanding these points helps us predict how the materials will behave in real world situations, like in construction or manufacturing. So region origin to A, alright, which is called the elastic region. O to A is the elastic region. You can see in the diagram here that this line is the initial straight part of the curve. In this region, the material behaves elastically, meaning it will return to its original shape if we remove the force. Alright, O to A. So curve is a straight line, O to A. This tells us that the relationship between stress and stress is linear. In other words, if we double the force, the extension or deformation also doubles as long as we stay within this region. So here stress is directly proportional to strain. That means if we write stress is equal to K into strain, where K is a constant, this relationship holds true. So this reason is where the Hooke's law applies, where Hooke's law states that the force needed to extend or compress a spring by some distance is proportional to that distance. So body regains its original dimensions when the applied force is removed. Alright. So next here in this region origin to A, elastic region, the solids behaves as an elastic body. That means it can return to its original shape after the force is removed. A point A on the curve is known as proportional limit. This is the highest point where the stress and strain are directly proportional to each other. Alright, A point is the highest point. At A, Hooke's law is still obeyed. We are continuing understanding stress strain curve. So next, reason A to B. Alright, A to B. So now focus on the reason from point A to B, which is called the non-linear elastic reason. Non-linear elastic reason. You can see here this highlighted in the diagram or figure 8.2, A to B. Alright. In this part of the curve, the relationship between stress and strain is no longer a straight line. Meaning the material's response is not directly proportional to the applied force. So notice here that stress is no longer proportional to strain. This means if we double the force, the deformation does not double. However, even in this non-linear region, the body will return to its original shape once the load is removed. So, let's discuss another points. Point B is the yield point, alright, or elastic limit. This is a critical point because it marks the maximum stress that the materials can handle and still return to its original shape once the force is removed. Emphasize that up to this point the materials behave elastically. At the yield point, something important happens. If we increase the force beyond this, the materials will not regain its original shape or size after removing the force. This means the materials has started to deform permanently, and which is called plastic deformation. So the stress value at point B is called yield strength of the material, often write as a sigma y. Yield strength is measured in pascals in SI units. It tells us how much stress the material can withstand before it starts to deform permanently. For example, if a metal has a yield strength of 250 million pascals, it can handle that much stress before it yields. This transition from elastic deformation to plastic deformation is a key concept up to the yield point. The material can recover, but beyond it changes the permanent. So, let's focus on analyzing the key points on the of the stress strain curve. So here, region B to D, plastic region. So we are looking at the region from point B to D on the curve, which is called plastic region. Notice the figure 8.2 showing a typical stress strain curve for a metal. In this region, the materials no longer return to its original shape when the force is removed. If we increase the load beyond point B, you will see that the strain or the amount of material stretches increases very quickly, even if we only add a little more stress. This means the materials is becoming much easier to stretch and it's starting to lose its ability to return to its original shape. If we remove the load at point C, uh, which is still in the plastic region, the material does not go back to its original length. The path the material follows when the load is removed from point C is shown by the dashed line from C to O. C to O prime. Alright. C2 all prime. This line shows that the materials does not return to its starting point, which means some permanent change has happened. The strain that remains after the load is removed is called permanent set, right? This means the material has a new shape or length, even though there is a no force acting it anymore. In this situation, even when the stress is reduced to zero, the strain is not zero. All right. This tells us that the material has been permanently deformed. It's a key point to remember. In plastic reason, removing the force does not undo the stretching that has already happened. When this happens, we say the material has undergone plastic deformation. This means the material has changed shape in a way that can't be reversed just by removing the force. We are continuing understanding stress strain curve. So, point point D, ultimate tensile strength sigma u. So let's look at point D on the curve, which is called the ultimate tensile strength, often written as sigma u. This is the highest point on the curve, showing the maximum stress the materials can handle before it starts to weaken. The figure 8.2 here shows a typical stress strain curve for a metal, and you can see point D marked as the peak. Alright, remember, ultimate tensile strength is measured in newtons per square meter, just like stress. At point D, the materials is experiences the maximum stress it can withstand. This means if we try to pull and harder, the materials won't be able to take it and will start to fail. Beyond point D, something interesting happens. The wire starts to form a neck, which means it uh, gets thinner in one spot. After this, even a small extra force can cause a lot more stretching, and the materials is close to breaking. So, point E, fracture point. So now let's focus on point E, which is called the fracture point. You can see figure 8.2. That's there here. Materials finally breaks after being stretched. Notice how the curve ends sharply at this point. This shows us the maximum strain the materials can handle before it snaps. If we keeping stretching the wire beyond point D, the strain keeps increasing until the material breaks at point E. This means the materials is no longer able to return to its original shape and it eventually fails. So, different properties of materials. Now we will learn. So first, let's talk about the ductile materials. Ductile materials are a special category of solids that can undergo significant deformation before breaking. So ductile materials are defined by having a large plastic region. The plastic region is the part of the stress strain curve where a material deforms permanently and does not return to its original shape when the force is removed. This means ductile materials can be shaped or stretched a lot before they finally break. So, ductile materials can undergo a large permanent strain before fracturing. In other words, after the plastic limit is crossed, these materials keep stretching and changing shape without snapping right away. Some common examples of ductile materials are copper, aluminium, and iron, wrought iron, because they can be bent, stretched, or drawn into different shape without breaking easily. A key feature of ductile materials is that they can be drawn into wires. This process is called ductility, and it's why metals like copper are used for electrical wiring. The ability to stretch into long, thin wires without breaking is essential for many engineering and technological applications. So, brittle materials. Brittle materials have vary differently from ductile ones. We will see how their response to force makes them suitable for some uses but not for others. Brittle materials have a very small plastic region. This means they don't deform much before breaking. As soon as the force exceeds a certain limit, called the elastic limit, these materials fracture almost immediately instead of stretching or bending. Brittle materials fracture soon after the elastic limit is crossed. Examples of brittle materials include cast iron, glass, and ceramics. These materials are strong under compression but weak under tension or bending. So, different properties of materials. We will continue here. So, now let's talk about the elastomers. Elastomers are materials that can be stretched to produce large strains, meaning they can change shape a lot when a force is applied. A common example is rubber. The figure 8.3 here shows the stress strain curve for the elastomer tissue of the aorta, which is a large blood vessel that carries blood from the heart. Look at here how this curve looks different from what we see in metals. So let's look at some key properties of elastomers. These are special because their behavior under stress is quite unique compared to the other materials. So first, notice that the stress strain curve for elastomers is not a straight line. Yes or no? Even for a small deformations, this means that the relationship between force applied and the amount of material stretches is not directly proportional. Another important property is that elastomers return to their original dimensions when the force is removed. This means they are highly elastic. And elastomers do not have a well-defined plastic region. In most materials, after a certain point, they undergo permanent deformation and do not return to their original shape. But with elastomers, there is a no clear point where this happens. They remain elastic over a wide range of strains. Examples: elastic tissue of aorta rubber. Now we will understand the concept of elastic moduli. So let's start with Hooke's law. Hooke's law tells us that the amount of stress a material experiences are directly proportional to the strain it undergoes as long as we don't exceed the material's elastic limit. In simple terms, if you pull or push or something like a spring, it will stretch or compress in a predictable way, but not but only up to a certain point. In the proportional region of the stress strain curve, which is within the elastic limits, stress increases in direct proportion to strain. So we can write this relationship as stress is equal to K into strain, where K is the proportionality constant called modulus of elasticity. It tells us how stiff or flexible a material is. A higher modulus means the material is stiffer and does not deform easily. while a lower modulus means it's more flexible. So we are continuing the concept of elastic modeling. So let's start by defining modulus of elasticity. This is the ratio of stress to strain. Stress is the force applied per unit area measured in newtons per square meter, and strain is the relative change in shape or size which has no units. So modulus of elasticity, often written as K, uh, tells us how stiff or flexible a material is. So K is equal to stress upon strain. Uh, the value of modulus of elasticity depends on the nature of the material and how it's being deformed. Finally, let's look at the units. The SI units of for modulus of elasticity is same as that for stress. Newton per meter square or Pascal, written as Newton per meter square Nm whole raised to the power minus 2. Now, Young's modulus. Young's modulus is a measure of a material's stiffness. It tells us how much a material will stretch or compress when a force is applied, as long as we stay within its elastic limit. In simple terms, it's the ratio of longitudinal stress, which is the force per unit area, to the longitudinal strain, which is the relative change in length. Now, let's look at the mathematical formulation. Young's modulus represented by the letter Y, which is equal to longitudinal stress upon longitudinal strain. Here, stress is measured in newtons per square meter or pascals, and strain is a ratio, so it has no units. It's a unitless. This formula helps us compare the stiffness of different materials. So we can also write this as Y equal to sigma divided by epsilon, where sigma stands for stress and epsilon stands for strain. Remember, a higher value of Y means the material is stiffer and resists deformation more. So we will continue Young's modulus. So let's start with mathematical deformation. We know already Y is longitudinal stress upon longitudinal strain. So longitudinal stress, we know force upon area, where F is the force in newtons and A is the area in square meters. This tells us how much force is acting per unit area. Longitudinal strain, delta L upon L. Strain has no units because it's a ratio of two lengths. So let's combine these formulas. So Young's modulus Y is the ratio of stress to the strain. So we write Y equal to force upon area and divided by delta L upon L. This formula shows us that Young's modulus depends on both the force applied and how much the material stretches. So by rearranging the formula, we get Y equal to force into length, force into L divided by area into delta L. This is a very useful form because it tells us to calculate Young's modulus if we know the force, original length, area, and change in length. Remember, SI unit for Young's modulus is the Pascal, just like pressure. Now, let's start by looking at the units of Young's modulus. Since strain is a ratio and has no units, the unit for the Young's modulus is the same as that of stress, which is Newton per meter squared or Pascal. This means whenever we calculate Young's modulus, we express it in Newton per meter square or Pascal, just like we do for pressure or stress. Uh, Higher value of Young's modulus means the materials is more elastic. In other words, it resists changes in its length more strongly when a force is applied. For example, steel has a much higher Young's modulus than rubber. So steel is much harder to stretch or compress compared to rubber. So let's look at table 8.1, which shows the Young's modulus and yield strengths for some common materials. For aluminium, copper, iron, and steel. Alright. So here, notice how steel and iron have much higher Young's modulus value compared to aluminium, meaning they are stiffer. Also compare the here yield strength, and this tells us how much stress material can handle before it starts to deform permanently. Alright. So aluminium Young's modulus 70 and steel 200. Copper 110 and iron 190, and respectively their ultimate strength and yield strength. So table 8.1, Young's moduli and yield strength for some material, and glass, concrete, wood, bone, and polystyrene. So Young modulus for glass 65, concrete 30, wood 13, bone 9.4, and polystyrene 3. Alright. So notice that Young's modulus measured in newtons per square meter and tells us how much a material resists being stretched. For example, glass has a high Young's modulus of 65 into 10 raised to the power 9 Newton meter square, meaning it's very stiff, while polystyrene is much less stiff at 3 into 10 raised to the power 9 Newton per meter square. The table also lists density, ultimate strength, and yield strength, which helps us compare how strong and heavy these materials are. Example 8.1. Structural steel rod has a radius of 10 mm and a length of 1.0 mm. A 100 kilonewton force stretches along its length. Calculate A. Stress, B. Elongation, and C. Strain on the rod. Young's modulus of structural steel is 2.0 into 10 raised to the power 11 Newton per meter square. So, first let's list out all the information provided in this problem. So radius of the rod R equal to 10 mm, length of the rod L equal to 1.0 meter, force applied 100 kilonewton, and Young's modulus for structural steel Y equal to 2.0 into 10 raised to the power 11 Newton per meter square. So let's assume that the rod is held by a clamp at one end and the force F is applied other end parallel to the length of the rod. This is a classic example of tensile stress. Look at the figure, which shows the direction of the applied force and how the rod is fixed in the place. Alright. First, we need to calculate the cross-sectional area of the rod. The formula for the cross-sectional area of a rod is A equal to pi r square, where r is the radius. So just put the values. A equal to pi into 10 raised to the power minus 3 meter whole square, and solving this you will be get A equal to 3.14 into 10 raised to the power minus 4 meter square. So now we will calculate stress. So we know stress is force upon area. If we talk about the definition, so we can say defined as force divided by area, or stress equals to force divided by area. Here F is the force applied in newtons and A is the area of cross-sectional area in square meters. Now let's substitute the numbers. The force is 100 kilonewtons, which is 100 times 10 to the 3 newtons, 10 to the power 3 newtons. Alright. So solving this calculation, you will be get the stress. Now, uh, let's focus on calculating stress. So stress is equal to 31.8 into 10 raised to the power 7 Newton per meter square. So it will be approximately 3.18 into 10 raised to the power 8 Newton per meter square. Next, we will calculate the elongation of the rod, which is how much it stretches under the applied force. We will use the formula for Young's modulus, which relates stress and strain. Here, Young's modulus represented by Y is a measure of the stiffness of the material. The formula rearranged gives us delta L and change in length as delta L equals F times L divided by A times Y. So just substitute the values into the formula and you will be get the value of delta L. Alright. So solving this, we will be get delta L. So let's focus on the elongation, which is the increase in length of the rod when the force is applied. So delta L is equal to 1.53 into 10 raised to the power minus 3 meter. So delta L is approximately 1.59 mm. So the rod stretches by about 1.59 millimeters under the applied force. Calculation of strain. So strain is equal to delta L by L. Strain equal to 1.59 into 10 raised to the power minus 3 m divided by 1 meter. Alright. So strain equal to 1.59 into 10 raised to the power minus 3. Solving for strain. To convert into percentage, multiply by 100. So strain equal to 1.59 into 10 raised to the power minus 3 into 100. So solving this, you will be get the value of strain. So strain is 0.16%. Summary. Stress strain curve is a graph showing the relationship between stress and strain, revealing a material's elastic and plastic properties. From point O to A, in this region, stress is directly proportional to strain, which means if we double the force, we stretch also doubles. Stress is also doubles. In region A to B, here the material still behave elastically, meaning it can return to its original shape, but stress and strain are not longer directly proportional. Point B is called the yield point or elastic limit. Beyond the yield point, region B to D, the materials undergoes plastic deformation, leading to a permanent set even after the load is removed. Point D represents the ultimate tensile strength, the maximum stress material can withstand before necking and eventual fracture. Point E is the fracture limit point where the materials breaks with the region between D and E being the plastic region. Ductile materials have a large plastic region. Brittle materials fracture quickly, and elastomers can endure large nonlinear elastic strains. Modulus of elasticity K is the proportionality constant in Hooke's law, defined as the ratio of the stress to strain with units of Newton per meter square or Pascal. Young modulus is the specific elastic modulus defined as the ratio of tensile stress to the longitudinal strain. Young's modulus can be mathematically expressed as y equal to FL divided by A into delta L, where a higher value of indicates greater material stiffness. Now, practice questions. First, if a wire of cross-sectional area 2 mm square is structured by a force of 100 Newton and its strain is measured to be 0.002, calculate the Young's modulus of the material. Second, Young's modulus of steel is 2 into 10 raised to the 11 Pascal. If a steel wire of length 2 meter and cross sectional area 0.5 mm square is subjected to a force of 100 Newton. Calculate the extension in the wire. A material follows Hooke's law up to a stress of 4 into 10 raised to the power 8 Pascal. If the Young's modulus is 2 into 10 raised to the power 11 Pascal, what is the strain at the proportional limit? A wire has a original length of 1.5 meter. When subjected to a tensile force, its length becomes 1.503 meter. Calculate longitudinal strain. If a force of 50 Newton produce a stress of 2.5 into 10 raised to the power 5 Pascal in a wire, what is the cross sectional area of the wire? Alright, so these are the practice questions and these are homework. Thank you for your attention. I hope all concepts are clear. Thank you.